In the last video, we introduced the four main electrical properties and talked about some mathematical relationships between them. In this video, we're going to introduce the concept of a circuit, but we're going to keep it pretty conceptual. We're not going to get into the math just yet. We're going to talk about how circuits are designed and how we're going to make some measurements based on those circuits. To start off, if you look in the IB Physics data booklet, there is an entire page devoted towards circuitry symbols. If you're going to draw a circuit as a scientist or an engineer, you're not going to draw it as this perfect photorealistic version of what's going on in real life. Instead, the picture that you draw is just comprised of a bunch of symbols that are stitched together to show the circuit that you're trying to describe. The symbols will allow us to create what we call a schematic diagram. The page in the IB Physics data booklet is a page of circles. This is your key to understand what the different symbols mean. So here you can see a cell, battery, some different voltmeter, ammeter, a lot of different resistor elements, capacitors, diodes. We're not going to use all of these in IB Physics SL, but many of these are going to be used in some fashion. Let's go ahead and build a little simple schematic circuit. To start off, we need to have some sort of voltage supply. Typically, we'll use like a battery to do that. And a battery is just a combination of just cells next to each other, one after another. So simply, we'll just use a cell to represent a power supply in this case. Officially, it's probably several in a row, but one will be enough to indicate what we're talking about. We'll also add in a switch here. The diagram for a switch looks very similar to what an actual switch looks like. It's just a conductor that isn't connected yet. So if you connect it, it closes the circuit and then it starts to flow. And then we'll add in a simple resistor. In the IB world, a resistor is represented by this rectangle. We'll talk about some other different ways that you've maybe seen resistors before as well. Now, right now, this isn't a circuit. This is just a combination of three different things all drawn together. To make it a circuit, we need one continuous loop that loops from one end of the cell to the other. So it's connecting each terminal of our battery. Now, this is not a circuit that anything's going to flow through yet because it's not a closed circuit. I've not closed my switch, but it has all the components that I need. It has a cell, a power supply, giving us a potential difference of voltage. It has a wire, a conductor here that allows current to flow, and it has some sort of resistance provided by this resistor here. If I close this switch, I can make some charges flow. Now, it's a common misconception that people think that the charges, the electrons that flow through a circuit, come from the battery or the power supply. Or if you plug something into the wall, there's a bunch of electrons that come streaming out of the wall. And that's what the current is. Well, that's part of the current, but the most of the current that's happening is charges that already exist in the conductor. Plugging it in or closing the switch just allows a push to push all of those charges through together. It's kind of like if you have a garden hose that's already filled with water and you turn on the spigot. You're not going to get out one end of the garden hose something that directly came from the spigot right away. Instead, it's just pushing the water that's already in there. So if I close this switch, these electrons that already existed in the wire start to move. And they all move together through that wire. The electrons aren't passing each other in very dramatic fashion. Maybe there's some jostling around, but in general, they're all moving at about the same velocity through that wire. Now, looking at this battery, these two parallel lines, you'll notice that one is longer than the other. The long side indicates the positive terminal of the battery, which means the short side indicates the negative terminal of the battery. If you think about the nature of an electron, you probably are familiar with the idea that opposites attract like charges repel. So if these are electrons and they are negatively charged, they are attracted to the positive side of the battery and repelled from the negative side of the battery. So the direction of the electron flow is what you would expect based on your understanding of how charges interact with each other, positive and negative. Looking at this battery, it's essentially like this. You might be aware of which side's the positive end or negative end of that battery. So if we were to draw it photorealistically, that's what that would look like. So this electron flow, in this case, in this diagram, is going counterclockwise. If I flipped the battery, it would flip the direction that the electrons flow. Well, one awkward, kind of annoying thing in just the nomenclature and terminology in circuits is this is not actually how we define the direction of the current, which is odd because this is the direction of the electron flow. But what we call conventional current is technically the direction that a positive charge would flow. We talked in the last video that the positive charges don't flow. They're stuck in the nucleus of the atom. But Ben Franklin thought that they were the things that flowed. So he defined current as the direction of flow of the positive charges. And that's been baked into just the nomenclature and definitions of circuitry and understanding of electricity since then. So when we draw the direction of conventional current, it is the direction that the positive charge would flow. Right now in this unit, honestly, it's not going to make a huge difference. It will a little bit when we get into force fields and the right-hand rule and forces that come from a current carrying wire. So I'll introduce it now, but we'll revisit it later on. All right. So resistance in a circuit, there's a lot of different components that act as resistors. All of these are technically some form of a resistor here: variable, potentiometer, thermistor, light dependent resistor, or a lamp. We'll talk about all of these in some capacity. You may have seen resistors before in a previous physics or physical science class drawn like this little squiggly line. That is still an eligible way of drawing a resistor as well, and a lot of diagrams that you'll see will have this form of resistor. That's the same thing as this simple resistor here in the rectangle. Sometimes we'll also draw resistors as little light bulbs just to allow us something that feels a little bit more tangible. Technically, a resistor is just something that resists. You don't get anything productive out of that. It just changes the overall structure and flow through your circuit. But a light bulb is also a form of resistor. This little filament here has a lot of resistance because it has such a small diameter. So that high resistance makes it harder for electrons to flow through that as well. So sometimes we'll use light bulbs because that allows us to see the current a little bit easier. Now, electrons are going to flow in a way that is based on how the resistors and the resistance of the circuit is set up. They typically will follow the path of least resistance. So a good diagram here is, here I've got this circuit that's going through that I can totally break. You'll notice here, right now, there's a broken circuit here, that this isn't connected, so there are no electrons flowing there until it's hooked up. Once it is, that pathway has no resistors on it. So instead of traveling through this path with the resistor, the electrons bypass that pathway entirely and just flow through the one with essentially no resistance. This is known as a short circuit, and it is the most dramatic example of this, where all the electrons are following that path of no resistance. Most cases are going to be some variation on this, that electrons will still flow in both pathways, but just to different extents, and we'll see that in a little bit. But the electrons were more likely to follow the path of least or lesser resistance. If we're going to combine more than one resistor in a circuit, which is kind of the key of a circuit, most circuits aren't just one component. There are a couple different ways that we can combine those. The first is we can place them end to end. So you just keep adding them one after another in that conductor. So R1, R2, or R1 through 3. We can keep going up to 100. This would be known as a series combination. They are connected one after another in a continuing series. Another way that you can connect them is in separate branches. Here we can do R1 and R2 on their own pathway, or you can keep adding pathways, R1, R2, R3, and so on. We call this a parallel circuit. And kind of that makes sense. You see these parallel lines. These are next to each other, kind of following parallel to each other. Now, most circuits are actually some combination of these. These are the most simple if everything's series and everything is parallel. So let's look at a couple examples of what that means for us. If we have resistors that are in series with each other, the circuit has these charges that are flowing through, and they flow all together. That there is not one resistor that's going to receive more current than another, because they are in the same line. That the flow of charges has to be the same all the way through. It's kind of like a little parade of electrons, that you can't have some electrons in the back going faster than the electrons before them. They can only take the place that is been left by an electron ahead. Another good example here is by using something called snap circuits to make a very simple example of a series circuit. I have here a series circuit. I know that it's a series circuit because each light bulb is connected in one singular path with the power supply. Because of that, if I close this switch and turn it on, both light bulbs light up, because now there is a continual path for those electrons to flow. It also means that if I unscrew one of these light bulbs, both light bulbs go out, because I have broken the circuit at that location. And the same thing holds true if I unscrew this one over here, both light bulbs will go out. So you'll notice that's also a great example for why it's super annoying sometimes in old Christmas light strings. When one light bulb goes out, if they are connected in series, all the bulbs go out, and you don't actually know which one it is that's the culprit to make the entire string of lights go bad, because if they're connected in series, one weak link blows the whole loop. Couple of key things to note in series here is that components are in one singular pathway, that there's only one way to flow through there, and because of that, the current flows through everything in the same way. Each resistor in series receives the same current. The other example is a parallel circuit. There's more than one branch. A good diagram of this I'll animate here. You'll notice that these charges can flow through either branch. So they kind of take turns going through each one and then coming out the other side. You'll also notice, if you look through here, a key feature is that the current ahead of time is faster than the current after it splits up. So the current is smaller in each branch than it is in the overall. And that's kind of the same thing if you had a river that split up into more than one. The current in each one is smaller, but they add up to the overall current. So here's an example of using that in snap circuits. I have here a simple parallel circuit. I can tell that it's a parallel circuit because there are two separate branches through which the current can flow. If I flip on the switch by closing the switch, current can now flow through this stretch here, and then here it splits off at this junction point into two separate pathways. I can flip on or off these switches here, and it controls only the light bulb that is on that branch. That also means if one of these light bulbs were to burn out or become unscrewed, the other light bulb is unaffected because there is still a branch, a pathway through which this current can flow. So you'll see that that's a much nicer way of connecting up lights if you were trying to make it so that one light doesn't control the fate of the entire string of lights. But there's a certain limitation. If you had a string of 100 lights, it would be crazy to have a bundle of 100 wires running to each bulb individually. So most strands of lights are some combination of series or parallel as they go through. Now, a couple things that you need to remember for parallel is that they are separate branches, and the current splits up between those two different pathways, or 3 or 4, or however many pathways you have in that branch. So getting back to this idea of current or charges flow or go towards the area of less resistance. If you look at this diagram here, this animation, you'll notice that this isn't a perfect short circuit. We aren't totally bypassing one of the branches because both have a resistor on them. But these resistors, unlike the animation on the last slide, are not equal to each other, which means that the current flowing through each of them is different. So which one of these branches do you think has less resistance? The one on the top or the one on the bottom? Which one makes it harder to flow? So if you think about just the idea of resistance, if you're trying to run through air or run through water, you're going to travel slower through the one that pushes back on you more. So if I reveal the actual ohm resistances here, the one on the top of the simulation has 20 ohms, the one on the bottom is 60 ohms, which means that it travels about 3 times slower than the one on the top. And we'll see that when we get into calculations of these and actually calculating the numerical quantity of that current. So a great model to understand this is something called the water flow model, is often referred to, because it's hard to visualize and it's impossible to actually see the charges that are flowing through a wire. So instead, you can think of it as water flowing through. And if we do that, a great analogy here for the different batteries and components that are using the voltage is to think of water flowing through and a pump pumping this water up to a higher elevation. It flows through at this higher elevation and then flows down through a series of different components, kind of these waterfalls or these ramps. This pump pushing them up, giving them some extra energy, that is essentially our battery. It's creating this potential difference, in this case, gravitational potential difference, elevating them up here. As it goes through each of these resistors, it loses some of that potential and then goes back down to eventually be down back at the bottom where the battery can lift it back up again. So this here is a series connection. Both of these resistors are one after another. An example of a parallel connection with the same sort of model is this, where there's 2 different branches for these charges to flow through either this 30 ohm or this 10 ohm. So using this, let's talk about how we're going to actually measure these circuits, measure these properties. It's nice to read out on the resistor how many ohms it is. That's pretty handy. But to actually measure a circuit, we need some way of seeing what the voltage or the current in amps is flowing through that circuit. When we measure it, there are a couple different tools that we could use. We could use this one here. This is known as a multimeter. It has a lot of different sensors in it. Depending on how you turn this dial, you can measure in different ways based on the circuitry inside. Instead, what we're going to typically be drawing is a pure voltmeter or a pure ammeter. A voltmeter obviously measures voltage. We're going to describe that. The schematic diagram for that is just a circle with a V in it. And an ammeter is a circle with an A. That measures amps or current. The way that you hook these up is different because they're measuring different things. So let's talk about how you would hook them up to a circuit to measure what you want. For an ammeter, you're going to hook this up to measure the flow through this circuitry. You have to hook it up in series with the component being measured. So if I wanted to know the current flowing through these resistors here, I would hook up this ammeter in line with those resistors. Right now it's not in a straight line, but that's fine because it's in the same wire flowing through. Essentially, to think about it, the current has to flow through this ammeter for the ammeter to measure the current that's flowing through it. Kind of makes sense. It's reading out how fast the current is flowing through that tool, that device. To see this in a simulation that we'll be using a little bit later, I have connected actually 4 different ammeters here. All of them are in series with these components. So we've got current of 3 amps, 3 amps, 3 amps, 3 amps. That also makes sense. We saw before that the current flowing through each component in a series circuit is always the same because there is no branch for that current to split up and get smaller or larger. This diagram here is the same as this diagram here. There's just different ways of showing that. And you'll notice in this animation that we saw earlier of the water flow model that all of these charges are moving at the same rate. They are all moving at that same current of 3 amps in this case. If we were to try to measure current of a parallel structure, you'll see here that as these charges get to this junction to split off into either this lower branch with 10 ohms or this upper branch with 30 ohms, there is a different current flowing through each. So to measure that current, I just hooked up an ammeter in series with the resistor on that branch that I want. So just put it on the branch and you can see the current flowing through that branch. So this 3.2 amps, splits up into 0.8 and 2.4. We'll see later on these two add up to 3.2, and that makes sense because that's the current that came to that junction. The way we see this in this water flow model, you'll notice that the current, the number of charges per second going through the 10 ohm is higher than through the 30 ohm, which represents the higher current through the 10 ohm than the 30 ohm. Now, if I want to measure voltage with a voltmeter, it's going to look a little bit different. A voltmeter has to be hooked up in parallel with the component that's being measured. So if I want to figure out the voltage being dissipated or provided by any component in this, I have to hook up my voltmeter with one lead on either side of the component I'm trying to measure. So if I want to measure the voltage being used by this resistor, I hook up one side to one side of the meter and the other to the other. So basically making a branch around that component. I could do the same thing on this other resistor. I would just hook it up like this. So one way to think of it is to measure the potential difference. You need two locations that you're connecting this up to, and you're looking at the difference before and after this component, essentially. To look at this in a simulation, if I want to measure the potential difference around this 30 ohm resistor, I connect up these two leads on either side. Here I can connect both leads around this 10 ohm resistor, and you'll see I got 90 volts, 30 volts. If I do both of them, it adds up to 120 volts, which is the same as if I were to connect both sides up to the battery, either side of the battery. The battery supplies 120 volts in this case. That's a pretty insane battery. The way that we see this in this diagram is to think of the voltage as being the potential difference, the height of this ramp. So if we were to think of it here, the height that this battery lifts it up is 120 volts. As it goes down this 30 ohm, it loses 90 volts, and then the other 30 volts. So the height being represented here, that's why more height is lost in the 30 ohm resistor than the 10 ohm, because it's using more voltage from that initial potential difference that was provided. To see this in a parallel circuit, if I hook up both sides, I see 24 volts of this total 24 that was provided. If I hook it up to the other branch, I see 24 volts there as well. If I hook it up to the battery, I will see 24 volts there as well. A series or parallel circuit, each branch is going to receive the same voltage, and we'll talk about that later. Seeing this in the water flow model, you'll notice that the charges here stay at that same highest potential difference until they get to both branches, and then each resistor dissipates the entire amount of voltage that was provided to it. So they're each dissipating, in this case, that 24 volts that was supplying initially. They don't have different drop heights like we saw in the series circuit. Instead, they're each going all the way down to zero for the battery to lift them back up. So the main takeaways in this lesson is you should be able to describe the direction of conventional current. Remember that weird Ben Franklin positive charges direction compared to the movement of the actual charges that are moving through the circuit, the electrons. You should be able to identify component combinations as parallel or series and describe how the current is going to flow differently through a parallel or a series set of resistors. And then you should also be able to describe the setup to measure current and voltage in a circuit using an ammeter or a voltmeter, respectively.